Hello students, this is our last video in the series of G10, which are the angles of a polygon. In this lesson we'll be learning about tessellations. Well, I've already got written down here for you. A tessellation is just a repeated pattern that covers a surface. A repeated pattern that covers a surface. And I want to show you some tessellations here. Let me just switch screens with you. All I did was Google tessellation, and this is the variety I got. We've got stuff from very basic geometric tessellations over here, or that could even look like the tile floor in your bathroom maybe. A puzzle is a tessellation, to something known as an Escher-like tessellation. E.C.M.C. Escher is one of the greatest artists of our time, and he is known for his very detailed work on tessellations. So if you're interested, just Google search tessellations and you're going to find so many awesome pictures. In this lesson, you'll actually be making a tessellation, so you may want to go ahead and get some inspiration here. Well, there are different types of tessellations. A regular tessellation is a pattern made with only one type of regular polygon. One type of regular polygon. So you might think of a chessboard or a honeycomb. These are regular tessellations. A few more facts. The sum of the measures around any point or vertex must be 360 degrees, and I hope that makes sense. Right? Think of that checkerboard. Okay, here's just a little baby window of it. If this is the point, and we're going all the way around that point, you've got a total of 360 degrees to fill up around that point. So only regular polygons that have an interior angle, which is a factor of 360, will tessellate. All right, so let's look at a couple regular shapes, okay? Think about it. Let's start with an equilateral triangle. Using what we've already learned in this unit, we can find the interior measure. So if we have an equilateral triangle, maybe give yourself a little picture there. Okay, you know that that has a sum of 180 degrees. And if we split that sum into the three angles, each angle is 60 degrees. 60, 60, 60. So is this an image that would tessellate? Well, if our interior angle must be a factor of 360 degrees, then all we need to do is take 360 degrees and divide it by the interior angle. Here I get 6. So this is a big yes. It will tessellate, and it's going to take 6 triangles to do that. Let me see if I can pull out my art skills and show you. Let's say here's our point that we're working around. Let's start with 180 degrees. If I split that with 3 triangles, this is just a sketch. Let's say all of those are equilateral. Got 60, 60, 60. Now I'm going this way. Another triangle. And there's a third one. There we go. All right, it's just a sketch. But if each of these angles all the way around is 60 degrees, 60 times all 6 triangles that are there is 360 degrees. So it does tessellate. All right, let's try a square. You know what a square looks like. The sum of a square is 360 degrees. If we take that 360 degrees and split it between the 4 angles, you're going to get 90 degrees per angle. That is probably something you already knew. So each interior angle measures 90 degrees. So does it tessellate? Is it a factor of 360? 360 degrees divided by that 90 is 4. It is a factor. So yes, a square tessellates. It's going to take 4 squares to tessellate the plane around each given point. I don't even know if I need to do a better job than this. I think I'm just going to pull it right down here. My checkerboard is the example. All right, let's try a pentagon. Shapes are getting a little tougher, so take your time sketching it out. There's my pentagon. Maybe you don't remember the sum total of a pentagon. That one's a little tougher to remember. So if we need to go through, let's do that. The formula we're using here is S equals 180 times n minus 2. Well, the number of sides here is 5, so the sum is equal to 180 times 5 minus 2. That equals a total of 540 degrees. To find one of those angles, I would just have to split that into 5, which would give me 108 degrees per angle. Okay, well, let's see if that's a factor of 360. 360 degrees divided by that 108 is 360 divided by, the calculator's not working, sorry. 360 divided by 108 is 3.333333333. So 3 1/3? That doesn't make any sense. You could not have 1/3 of a pentagon and it still be a regular tessellation. So this shape does not tessellate. Okay. Let's keep going. Let's think about a hexagon next. Hexagon is 6 sides. 1, 2, 3, 4, 5, 6. Okay, if you don't know the sum total of that hexagon, go back to our formula. The sum is equal to 180 degrees times the number of sides, which is 6, minus 2. This sum is going to equal 720 degrees. So there are 6 angles to split that between, giving each angle 120 degrees. Let's see if that interior measurement is a factor of 360. 360 degrees divided by this interior angle measure is equal to 3. So it is a factor. It takes 3 hexagons to tessellate. Oh goodness, let's see if we can sketch that one out. All right, hexagon. Ooh, that's a pretty good hexagon. Right, I'm going to tessellate around this point here. Okay, so hexagon number 2. Not too bad. I'm pretty impressed with myself here. Hexagon number 3. Each of these interior angles is 120 degrees if we can draw a perfect hexagon, which none of us can do by freehand. But that 120 with 3 hexagons makes 360 degrees, which is why it tessellates. Let's try a couple more. How about a heptagon, a 7-sided figure? Really getting tough to draw now. 1, 2, 3, 4, 5, 6, 7. It's starting to look like a circle. Blah. Well, the sum is equal to 180 times the number of sides, which is 7, minus 2. 180 times 5, 180 times 5 is 900. So the sum here is 900 degrees to split between all 7 angles. So 900 divided by 7 is 128.571428,714, blah, 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 an irrational number here. Okay? So we can't have 57 hundredths of if we try to find out if that's a factor and we divide by that 128.57, 360 divided by that value gives us 2.8. We can't have 0.8 of a shape and it still be a regular tessellation. So this is absolutely not a tessellated figure. One more to think about. Here we go. An octagon. A little easier for me to draw. 8 sides. The sum of an octagon would be 180 times 8 minus 2. So that's 180 times 6 for a sum of 1080. I've got to split that sum between all 8 angles, which gives me 135 degrees per angle. Let's see if 135 is a factor of 360. 360 divided by this interior angle measure is 2.6 repeating. Again, guys, we can't have a portion of a shape. It has to be a whole to be a factor, so that's a no. So far, we've only found 3 shapes that tessellate. Well, guess what? Fun fact here. No regular polygon with more than 6 sides can tessellate. Therefore, these that we have listed above are the only shapes that tessellate. Jot them down. An equilateral triangle, a square, and a regular hexagon. These are the only regular figures that can tessellate a plane. That's important to know. On the back of the sheet, I've provided some SOL practice with tessellations. You can work that with a partner. You can come see me. I think we should do a couple together just so you know what it looks like, and then the rest you can do on your own. So flip over and let's look. What are our SOL writers asking us to be able to do here? Let's take a peek. Number 1, a regular pentagon and a regular hexagon share a side as shown in the figure. What is the measure of angle A to B to G? There's our question. So this is a tessellation. It's a tessellation with hexagons and pentagons put together. Well, we just did all this work on the front, so I'm not going to forget about it. We know that one interior angle measure of a pentagon is 108 degrees. So I'm going to write that in here. We also know that one interior angle measurement of a hexagon is 120 degrees. So I'll write that in here. We also know that a tessellation cannot have any gaps. It has to be a repeated patterns over and over and over again. And we know that the sum of the measures around any point has to be 360 degrees. So I've got 360 degrees total, and I've already used up 108 on the pentagon and 120 on the hexagon. So if I subtract those off, whatever's left over is going to be that leftover angle, 132 degrees. That's a great example of how you'll be tested on tessellations. Let's try one more. Let's skip down here to number 5. In this figure, it's composed of an isosceles trapezoid and a regular hexagon. Regular octagon. What's the value of x? Okay, well, grab your paper, flip over and look at the other side. We just did the work for a regular octagon. A regular octagon has an interior angle measurement of 135. So all of these interior angles of the octagon all the way around are 135. We also know that the sum of any quadrilateral is 360 degrees. Now this is not a regular shape. We've got 360 degrees built into this shape here, and they've used 55 and 55 for the base angles of this trapezoid. So 360, take off those two 55s, leaves me with 250 degrees. Because this is isosceles, there's a blast from the past word, the sides are equal, which means the angles here are equal. So this 250 degrees that's left has to be split evenly for 125 each. This question really is bringing a lot of information from the past back. Now we can get into the tessellation part. Around this single point is a total of 360 degrees. We've used 135 degrees for the octagon. We've used 125 degrees for the isosceles trapezoid. So what's left here is 100 degrees for our value of x. Okay, take a little bit of time and practice some of these other example problems. Come get them checked so that we can talk about them if we need to. I've also loaded a practice set up on Power Test so that you can get a couple more practices if you feel like you need them. And happy studying.